Hello, I'm Paulo Shakarian, and welcome back to the Neuro Symbolic Channel. And today we will be discussing what is perhaps the greatest challenge in neurosymbolic AI, the symbol grounding problem. So this lecture is a continuation in our series where we have explored the Kautz taxonomy, and in earlier lectures we looked at, in particular, let's get the laser pointer going here. Kautz 1, 2, and 4, and all of these variants of neurosymbolic AI that Henry Kautz classified here are focused on using neural networks to do reasoning. Today, we're going to talk about symbol grounding, and this will lead us in later lectures to talk about Kautz 3 and Kautz 5. But we wanted to step away from going into the different parts of the Kautz taxonomy and focus on symbol grounding itself. So, and we'll talk a lot about what philosophers call the symbol grounding problem that we'll define shortly. So, failure of symbol grounding is, happens when symbols are not properly grounded in perception. So here we see from an old paper example of something could happen in an adversarial case where this car has some kind of pattern on the hood, and it causes a vision model to recognize as a cake instead of a car. And these types of adversarial examples have been around for years, and this is a very active area of research. But the adversarial issue aside, what has happened here is the symbol cake was improperly grounded in perception. And so going back to our notions of dual process theory and where symbol grounding comes into play here is if you start to ground something using your autonomous system, so quick perceptions. So you're walking down the street in, someplace other than Syracuse, New York, and you see a person that looks like me, and you might say, "Oh, that's Paulo," but then you'll stop and you'll correct yourself, and you'll say that can't possibly be Paulo. Paulo is in New York. Now, what you've done is you've accomplished symbol grounding because you have put, because of the semantic meaning of the symbol and the contextual domain knowledge, you have taken that initial perception that had an error and you were able to correct it. So let's talk about an implementation example. And I'm going to bring this up a lot through this talk. Now, SATNet is a paper that looked to solve the Sudoku problem using a neural symbolic framework that was predominantly neural. So what you have is you have Sudoku, and one variant the authors were particularly interested in was what's called the visual Sudoku, where you have handwritten digits. There's like this digit classifier that the digits go through, and then it goes through the SATNet solution solver that for Sudoku and gives a result. Now, what the authors claimed was they said, hey, because that digit classifier was only 74% accurate, we were never going to get above that due to, or because the digit classifier was limited in accuracy, the best we could do for overall end-to-end was 74%. They stated their system got to 63, and that was pretty good. And so what you see here is you see a system where the SATNet model by itself was trained and tested on Sudoku problems that were represented as numbers, so not with any kind of image or anything like that. And then the idea with going to the visual version was, hey, we could just tack on this, CNN at the beginning, which will classify the digits, and it'll do a good enough job where our other model can actually solve the puzzle. However, subsequent results showed that these were overstated, basically due to some label leakage that occurred during the training process, and we'll touch on how that happened in a little bit. That's interesting all by itself. But bottom line is, when this was done correctly, doing it with this setup resulted in catastrophic failure. So you're talking about, when the outputs get masked, you're talking about near zero numbers. And so this is quite interesting because by itself, the non-visual version of this, both in the subsequent paper that tried to reproduce the results of the original, as well as the digit classifier, as components, these things work really great. But then when you combine them, the errors compounded too much and it led to catastrophic failure. So let's go back a little bit to some things we talked about earlier regarding distributed versus localist representation from the Garces and Lamb position paper from 2020 on the third wave about neurosymbolic AI. And I talk about neural systems use distributed representation where the values in the vector are spread out throughout the entire vector, and symbolic systems use a localist representation using very few components of the vector have something that's not a zero, usually just one. And then they went on to say that, hey, going from one to another, this is going to be a really tough problem. How do you turn these vectors that are inherently a distributed representation into something that is localist? The other thing to note here as well is that distributed representations are easier to learn than localist ones. But when you do reasoning, it's the localist ones that allow you to do things compositionally and ensure that you still get the right answer. So for example, when you teach a little kid how to do arithmetic, very quickly they can generalize arithmetic to larger and larger numbers if they understood the base concepts. Meanwhile, we saw, especially in the early LLMs that were just training to learn arithmetic, they would fail in weird cases where children wouldn't. There would be certain numbers that just would happen not to show up in like grade school math exercises on the internet, where it would fail at a very significant rate. Meanwhile, grade school children could accomplish the feats, going to arbitrarily large numbers. So this leads to a different view between the neural network versus symbolic side. And, one of the, kind of two schools of thought had emerged in the early days of artificial intelligence. And, the main line of thinking for many years was symbolic, and that's because that part of AI was born out of computer science, mathematics, and logic. And so when you look at a symbolic view of the mind, you look at manipulating these symbols. So doing things like arithmetic, doing things like inference and first order logic. However, on the other side, when you look at this from a neurological or a cognitive or a psychological perspective, you may say, hey, we want to represent things as neurons. People's memories work in an associative manner, which does not adhere to, the proof theory, for example. And so that's what gave rise to the connectionist view of things. So as we look at how to unify the two, it's important to define a symbol system. And we're going to rely on this classic paper by Harnad from 1990. And we'll go through his criteria of what a symbol system is, and then we'll show some examples of things that are or are not symbol systems. So the first criteria is you have a set of arbitrary physical tokens. And these tokens are manipulated based on explicit rules. And then these rules can produce, or these rules are themselves tokens or strings of tokens. Now, how those tokens are arranged in the rules governs the outcome of application of those rules. So it's inherently syntactic. You don't have to go back and reference to the underlying meaning of the symbols to use those rules. If all you see are the symbols and the rules, you can draw conclusions. And so these syntactic manipulations just hinge on combining and recombining the token symbols. And those token symbols are and the way those tokens are combined, you can have primitive or atomic symbols, and you can also have composite symbols or composite symbol token strings, which are just series of tokens based on the ruleful combination. But in this syntactic manipulation, all these manipulations should still be semantically interpretable. So that's the key thing. Even though I don't need to understand the meaning to do manipulations on the symbols, I can always be guaranteed that the meaning of the underlying result of the manipulation will adhere to the same semantics. And that's a really key notion. So we talked about arithmetic. You can write down addition as a series of rules based on, digits, the addition sign and the equal sign, and you can come up with a system for addition based on that just has these rules. And you could show, and you don't have to teach someone addition, you just have to teach them how to follow the rules. And they can add they can do addition as much as that requires. They would never know how it really works. But if you would check their work, it would always be correct because you specify the rules based on the underlying semantics. Let's talk about another example, and this is a version of a slide from an undergraduate course, propositional logic. And so, assuming existence of a set of ground atoms, the world is a subset of atoms. If the atom is in the world, it's true. If it's not, it's false. And then we have the semantics about, how a world satisfies an atom and so on. And so this meets criteria 1 and 6 because you have a set of arbitrary tokens and you have these primitive atomic symbols. Then as we build up propositional logic, we have conjunction where we can put two symbols together, A and B or F and A is true if a world satisfies both F and A. And then we can have rules. And so conjunctions, this is a way to do composite symbol token strings. Rules we have rules in the system that are also consisting of tokens and strings of tokens. And the rules can manipulate the system based purely on the syntax. I never have to look back at the meaning. And so I can do this ruleful combination. However, the way the satisfaction relationship is defined, I can be assured that for any execution of a sequence of rules, I'm going to have something that has valid semantics. So the simple example, propositional logic, is a symbol system. So here's just some examples from propositional logic. You say if it rained, the grass is wet. We say if we have a second rule that says if water is running and the sprinkler is on, then the grass is wet. And so we have different worlds, such as the grass is wet and rained, and we have sprinkler on and water running. And we can determine just by applying, the rules to to that set of atoms, we can quickly see if we run into something that, satisfies, if the world satisfies the rules or not. So the next example is DeepSeek R1, and this is not a symbol system. So let's take a look at it. Well, it's operating language, so that has tokens. So yes, it's operating on tokens, criteria 1. And if you read the DeepSeek technical report, you might see, okay, well, it's applying these rules to its output. So it's applying rules to tokens, and it's determining if, the output quality by the application of these rules. So maybe this is a yes to 2 and 3. But that actual answer is not so fast, because the model is acting in accordance to rules, but it's not following the rules. So if you read the DeepSeek technical report, especially what you see in here, so the format rewards, it's looking at a chunk of text and seeing that it adheres to a format, say JSON or Python code. The accuracy rewards are likely looking at things the same way. If there's a math problem or arithmetic in there and it says, 3 plus 5 is 27, it's going to flag that as an error. And so these rewards, they're not operating on individual symbols, they're operating on chunks of text. And this is something that is explicitly not part of a symbol system, because you can't operate on chunks of tokens, because you can't have semantic interpretability if you do that. And so as DeepSeek is applying its rules to chunks and not individual symbols, we don't have that semantic interpretability in the output. And one easy way to know that you don't have semantic interpretability is, if you did, you could avoid all hallucinations. And this would be essentially the same thing as being able to check if everything is correct. This is also why when you look at LLMs used in the context of a larger system, like in an earlier lecture we talked about AlphaEvolve, we see that is in fact a symbol system because of the way the LLM is used. And that's exactly what we're saying on the last point. When you use the words reasoning about, you're reasoning about what DeepSeek is doing here is it's reasoning about a language that is based on like properties of the text. And actually in my lab, this is something that we're actually working on. We're doing similar things to the strategy the DeepSeek people took, in that we're reasoning about things in the text by sort of lifting chunks of text into a symbolic language. Now, this doesn't mean that the underlying text itself is going to be accurate or the output of the LLM will be accurate, but it does mean that once we lifted things out of the text, as they do here, that reasoning about this kind of meta system is correct. But that doesn't ensure correctness of the overall system. So I mentioned AlphaEvolve. How can we know that that's a symbol system? Well, it is by Harnad's definition, because we know that everything here can be verified with respect to its meaning. And the verifiers in AlphaEvolve, they differ from the rules in DeepSeek, where the verifiers are actually reasoning about the LLM output and are used to ensure correctness, where the rules in DeepSeek R1, they're reasoning about the output, making sure it adheres to certain things, but this does not allow them to make statements about the correctness of that output. Now, of course, the logical language for this has to be known a priori, and that's usually some engineering work to get set up. Okay, connectionist system, this is much easier. Uh, and it has received different names over the years, such as bio-inspired system or neural networks. It's often compared to the brain, but whether or not a connectionist system is biologically plausible, it doesn't really matter. The main point is that it's inherently associative, where things are, where representations of an object are associated with other representations that maybe are some kind of prototype of a class of that object, and that's what's used to make decisions. And it relies on statistical structure um, of the underlying data that the representation is based off of. So the connectionists will often argue that cognition is not symbol manipulation. Humans do things associatively, and these patterns that we recognize and use to make decision, uh, they are based on activations of neurons that may have different strengths, and these can be adjusted on the basis of new input. Now, in the early days, there was some discussion on the connectionism itself as a subclass of a symbolic system, but based on what we see here, especially the statistical nature of it and the associative nature is we don't regard connectionist systems as in general meeting the above criteria, with actually the exception of Couch 4 systems like differentiable ILP that are sort of designed to precisely mimic underlying logic. But for today and going forward, that's generally not going to be what we were talking about. So here's a toy example. We have here the famous soccer player, Messi from Argentina. This input goes through a neural network. It recognizes him as Messi. It recognizes the Argentinian national team logo on his jersey, recognizes that they're World Cup champions. This slide was made by my Argentine colleague. So the system can correctly label things, but the argument here is there is no inherent knowledge about Messi. If it would have accidentally seen that Messi was wearing, say, uh, a Greek jersey instead of an Argentine jersey, it wouldn't realize that that was a mistake because it has no concept of any kind of semantic consistency underneath. And this is why we see these examples with noise, as we saw in the early slide, can be used to fool the system. So this may lead you to think, well, okay, maybe symbols are really much better, and we can make logical rules like this to understand things about, the soccer player and who his teammates are and what team they play on and so forth. And you can look at this logic program, you can draw conclusions and so forth. But if you just make these symbols from some kind of process, or if you didn't understand what any of those predicates or constants meant in the last slide because you're not familiar with soccer or the English language, it might as well look like this. And so here is another symbol system, but we've worked to divorce these symbols from the reality. And if you look at between this slide and the last, it is the same thing structurally. The difference is just what we call the symbols. And writing it this way was done to illustrate that symbols by themselves have no meaning. And this is a problem with symbol systems. They're not grounded in anything by themselves. And the symbol grounding problem is how do we go about doing that? And This is kind of the big idea that Harnad introduced in this 1990 paper. So let's take a little step back in time, a little before that, and let's talk about John Searle's thought experiment. And so, one thing that Harnad emphasized was that, hey, maybe this connection between perception and then symbols, maybe this is the key thing to human intelligence. And if we don't solve this problem, maybe we're not developing truly intelligent systems. And this was actually just a step in a long-going debate that was going on for about a decade, and it stemmed from something called the Chinese room argument. And so Searle challenged the core assumption of symbolic AI at the time, saying that a symbol system is not capable of generating behavior indistinct, that if a system was so let's talk about the Chinese room argument. And this is the problem that Searle introduced in the early 80s. And so the idea is, imagine that you're alone in a room following a computer program for responding to Chinese characters that are slipped under the door. You don't know anything about the Chinese language, but you follow this program that just tells you how to manipulate the symbols and then respond back with a string of Chinese characters. Everyone outside the room will suppose that someone who is fluent in Chinese is inside the room. But the person inside the room doesn't have an inherent understanding of the language. That's the argument. And at the time, this was an argument against symbolic AI from a philosophical perspective, that you cannot develop intelligence with symbolic AI because the meaning of the symbols is never fully understood. And gets to this point that symbol meaning, so just like when I showed the logic program about Argentina, when I showed the logic program that had Argentina and Messi written in it, you could understand what it was about, but information was not intrinsic to the symbols. It was parasitic on the fact that those symbols had meaning for you because in the previous slide you saw pictures of the soccer player. The symbols themselves don't have any intrinsic meaning. And so because of this, because the meanings of the symbols are extrinsic to them, manipulating symbols is not a viable model for intelligence. And so Searle's argument, because of this thought experiment, is that cognition cannot be just symbol manipulation. Now, again, the context for this is Harnad's paper was published in 1990, and this was a time during like an AI summer that was quickly turning into an AI winter, where you had these things called Lisp machines, and they were expert systems that could do symbolic manipulation, and they were very good at providing value to businesses, provided that business would hire someone who understood first order logic, and then and that the process of translating business information to that logic was done correctly. Now, a lot of businesses would like to pay for this once and then get a bunch of results and get return on investment, but they were sort of loath to hire someone to constantly maintain this. They felt that that was not worth doing. Anyway, but there were also failures too, in that one interesting thing is sometimes when these systems would fail, it would be due to a poor encoding of knowledge because someone messed up the definition of what a given symbol would mean, and so it produced garbage results. And this dissatisfaction with these results that were from the people or the engineer who was creating the first order logic somehow misunderstanding the domain expert led to these strange outputs. People like Harnad and Searle, kind of noticed that, hey, this is because the definition of the symbols is incorrect. So the notion here with what Harnad did is he was taking things from what Searle thought experiment said, and it says, well, hey, this cannot be done. And he turns it into a question of the symbol grounding problem and asking, how can we ascribe meaning to meaningless symbols that can be still manipulated based on, rules, and we arrive with semantic conclusions. And it's a really interesting question when you think about it, because again, as people, we do this all the time. We have meanings for the symbols that we manipulate in our heads. We can manipulate them in ways without having to think about those meanings, and we can be assured that the results are still going to have appropriate meaning. So later work identified a condition called the zero semantical commitment condition. And that was because once Harnad introduced that problem, so he introduced that problem, he has his solution to it that we'll talk about. Many others would complain about his solution and point out flaws and offer alternative solutions, and most of this occurred in the philosophy literature. And in 2005, there was a nice survey paper that summarized the results, claiming that basically, hey, no one's been able to solve this problem, and here's why. Because to truly solve the problem, you have to have what's called the Z condition. And you can't have any form of innatism. So you can't assume that the agent who is doing the symbol grounding has any innate knowledge about what the symbols mean. You give no form of externalization. So the agent can't have anything that allows it to look up what a symbol means. Now, all that said, the autonomous agent can have its own capacities and resources to ground the symbols. That's okay, but it can't violate, 1 and 2. And so anything that violates 1 or 2 is what's referred to as semantically committed. So what can happen here is you can imagine an agent moving around in a perceptual environment somehow and elaborating its own semantics on symbols that it manipulates, and somehow doing that from scratch or interacting with other autonomous agents. And so this can't have anything pre-installed in the agent, and that can't have any semantic resources outside of the agent, because that just assumes that there's someone or some other agent that is semantically proficient. And as I mentioned before, it does not exclude the possibility that it could have its own capacity and resources. Now, let's talk about some violations of this. So my view is the Z condition is very strict and maybe a little overly so. And so here's an example of what has been referred to as outside resources. So any pre-existing symbol system where the symbols are linked to a source of meaning. The presence of any supervised model is also still considered a violation, even though the supervised machine learning model in almost all cases does not produce symbols that can be comprised of a symbol system. Now, while self-supervision isn't mentioned explicitly, which would be like the use of foundation models, based on looking at some of these papers that stated when the Z condition is violated, this would likely also, violate the Z condition by what authors around this time who were studying the problem would suggest. So examples of a violation, using like specialized loss or reward function, guided by, logic, specialized representations, so, embeddings designed for a certain case, as well as encoding of priors. So even in the ARC challenge, if you're familiar with that, that's looking to have a test for AI systems to see how close they are to AGI. Even these problems still utilize a notion of a prior that makes them very hard to solve without having these priors. And that's such as things as containment or symmetries or certain shapes or notions of upscaling and downscaling. So the Z condition is, of course, very extreme. Now, some arguments against Searle include Dennett, who say that there is no such thing as non-derived intentionality. And he says that Searle's thought experiment doesn't differentiate humans from intelligent systems. And we would see that Dennett's stance would open the door to supervision or other similar techniques being used in the context of some type of agent system. Cummins, after Harnad, argues that symbol systems really arose because they're needed for communication, because in order to communicate, agents have to share semantics, otherwise they will be unsuccessful. And the assignment of meaning to symbols has mainly arisen due to communication. And he said, because of this, there's not really a symbol grounding problem. And so he talks about this notion of a meaning for. So we have a perceived cat, and it causes a certain part of our brain to be activated. And this symbol cat is then associated with our semantic knowledge about cats. And so also the word cat is associated with that same semantic knowledge. And that word cat, which is a symbol, has the same meaning for, so the spot in our knowledge, as the perceived cat. Now that symbol cat goes to maybe a little bit different portion of the brain for the other agent. So it has a different set of associations. But that symbol for the other agent is still associated with the same meaning, and other perceptions of cats that may be different from the first agent. Another person who would also agree with Cummings would be Hinton, who would also argue there is no symbols, as seen in this quote from MIT Tech Review. He believes that everything humans do is just arising from these vectors, and all the operations are being done on on some sort of underlying associative representation. So anyway, back to the symbol grounding problem is, even with supervision though, this is very difficult. And this was sort of a classic example from a few years back, where the results of image classifiers between the results of an image classifier between a dog and a wolf were examined, and it quickly became apparent that it was deciding if an animal is a dog or a wolf by the presence of snow, because the pictures of wolves all had snow in that particular data set. And also, as we saw with SATNet, even with supervision, we have a lot of difficulty. So here, the process was supervised. We had the model with, pre-trained weights that was really good at recognizing digits, but it wasn't good enough to provide input to a model that would solve the Sudoku problem. So what happens if we constrain our training with logic? Well, one view of this is to view that we have a neurosymbolic system and it identifies some higher level concepts based on lower level precepts. And we want the probability of observing some concepts given precept X to be the same as that for ground truth. So this is, kind of standard, right? However, we could have alternate parameterizations that could still occur in an optimized model. So here's our training data of the XY pairs. Here's some knowledge base. And so we have the loss function that is resulting from a maximization of the assignment of parameters. But we also at the same time have these underlying concepts that are not equivalent to the concepts in the ground truth given X. And this could be possible. And let's talk about how a reasoning shortcut happens. So here we see an example in something like a neurosymbolic system of a perception of a red light, and the concept red is one of the concepts there, and it's assigned to the light. And so the ground truth is stop, and the model learns stop. Now here, if the model sees a green light and a person walking in the street, and it assigns the person to the concept of red and the light to green, the result is the same. It stops, and that's in compliance with the ground truth. So it got to the answer that's in the ground truth, but it screwed up the concepts along the way. And so what happens if you go out of distribution and you have a rule that says something like, hey, if there's an emergency and there's no pedestrian, then you could go. Well, it sees the pedestrian as a red light. And so it can, the vehicle can go straight ahead, which of course is not what we wanted to do. Now, in the survey that introduced the Z condition, they grouped the work of symbol grounding into three categories: representationalism, semi-representationalism, and non-representationalism. And then all of these really were about seeking how to ground symbols based on the sensorio-motor capabilities of the agents involved. But all of these different types of methods turn out to be semantically committed. And so we'll talk a bit about the representationalist approach. So the idea is to solve symbol grounding by grounding the artificial agent's symbols and representations arising from its manipulations of the perceptual data. So, and how the paper proceeds, the idea is to capture some salient features shared by sets of the perceptual data, abstract these features from the sets, identify these abstractions as the contents of some kind of categorical or conceptual representation, and then use those representations to ground the symbols. Now, the main critique of this approach from Harnad was that came from the later work by Taddeo, was that they claimed it was guilty of circular reasoning. So this elaboration of how you group these features together from what is being perceived, they argue that presupposes that you have that semantic capability. But going back to the process, it can be viewed in three stages. You have this idea of iconization, so transforming analog signals into iconic representations and identifying things that are equivalent across some dimension. Discrimination, judging whether two inputs are the same or different by how much they differ. And identification, and this is assigning a unique response or name to a class of inputs. So the first two really deal with subsymbolic processes. So we could see that these are, have analogs in the machine learning literature. And the third is the process of identification where the symbols are actually grounded. So this iconic representation is obtained from the set of experiences relating to the perceptions of the object. So you could think of the autonomous agent as kind of a scientist who's experimenting in the real world. The categorical representations are obtained through this discrimination process. Through this, the invariant features of the iconic representation are identified. The elaboration process, and this is where this particular approach gets into a little bit of trouble with the Z condition, is when categorical representations are assigned to these classes of symbols, and which leads to the actual grounding. But inherently, like this is kind of one of the first, real neurosymbolic AI ideas that were introduced. He provides sort of a concept for it in this toy problem where he calls Perk, which is just this agent that is outfitted with a video camera and has some kind of neural network, but no semantic resources. And he says, hey, suppose it's able to produce these iconic representations and develop these categorical representations by somehow discriminating between things based on its interaction with them. And it can, and in the paper he talks about, well, suppose you can then put some kind of hierarchy of meaning, things like quadruped animal, and these are the meanings of the symbols. But again, this is kind of where it gets into trouble in this elaboration process when quadruped animal is assigned to it because, hey, where does it come from? And so you could say, how does that happen? I mean, an obvious answer is some kind of supervised neural network, but this is trained on data through backpropagation, so it has this extrinsic aspect of the Z condition because it's coming from the training data. Now, while I think on one side, I think this is a bit, overly restrictive definition of the Z condition. I also believe that the use of neural network in this way and just kind of, this is at the time in the 1990s, like, oh yeah, the neural network will get you this stuff is a little bit hand wavy because by itself, the output of the representation of the neural network is also prone to error due to the statistical nature of the model. And as we saw, once we started doing reasoning on results with SATNet, we quickly got to a zero accuracy. So the other, you know, in the critique of Harnad's proposal, the other thing is like, hey, if you're not using semantic knowledge, you must have some hard-coded or built-in biases about the nature of these representations and what they mean. So, so anyway, this results in an output that is semantically committed. So let's go back to SATNet. Now let's look at a follow-on paper. This is actually a third paper in all by different authors who studied this problem. And so here, we had this visual Sudoku problem, which is this, game where you play with a grid of numbers and you have to have the numbers add up to something in the different directions. And part of the problem with the original paper was this label leakage, where you have the input and output, and if the supervised, because of the training of the supervised model, you're leaking the output of the entire solution to everything downstream because you have output as these digits and not just as the ones you're supposed to fill in. So to mask this output, you'd only really care about what the zeros are replaced with. So to address this problem that was due to this label leakage in the original paper, and then when both Topan and the other research group before him that tried to reproduce the SATNet results found didn't quite work, the notion was, hey, let's use an unsupervised approach for the digit classifier. And so in some ways, you can think of this whole SATNet saga as a way of we've identified some additional semantic commitment that we felt was inappropriate for the problem. It still is much more semantically committed than what the philosophers talk about with the Z condition. But what's interesting here is that they're talking about, certain aspects of it and the semantic commitment that arises from not masking the other digits. When that, if it was properly working, you should get the same results if you mask those digits. So here the notion was, well, let's see if we can overcome this with a supervised learning process. So the notion was, well, hey, we assume that we have, some pre-trained encodings of the input digits, and they're related to the correct label encodings by some permutation. And so you could think of these encodings as symbols with no meaning. And matrix P is kind of giving us how meaning can be imbued to these meaningless symbols. And so, this assumption is that, hey, the same thing is the same relationship is going to hold true for, the ground truth. So how do we learn this permutation matrix? Well, they say, well, freeze the digit classifier, train the SATNet, which is the model that's used for actually solving the problem, with a special loss function that allows you to learn this permutation matrix. And you stop training it until it converges on P. Now you freeze P and you switch to traditional loss function. And now you learn the weights. And you unfreeze the digit classifier as well. So what's interesting here is the thing that they're learning is actually this matrix P is what's grounding the symbol. And this turns out to work very well. Back to kind of the philosophy standpoint is when you look at other approaches to symbol grounding problem, you have what's called the semi-representational approach, where now you have multiple robots converge on a semantics through a kind of game that they play, where the robots are communicating with each other to try to converge on a semantics. You have a non-representational paradigm, which is you have a student-teacher paradigm where agents ground symbols as a result of an imitation strategy. Uh, you also have what's called a practical approach, where you have robots are establishing action-based semantics and agents interact at an object at a meta level. And we'll touch on this a little bit next time. But really, all of these arguments have been made against all of these approaches. And, really there's kind of two things that come up. One is violation of the Z condition. The other is establishing a private language that is not interpretable outside of the agent or the set of agents. So as for concluding remarks, I'm listing here criteria proposed by Taddeo and Floridi in their paper surveying the different approaches to symbol grounding. What's interesting here is these criteria, they're largely algorithmic, and these are criteria that they landed on in kind of examining the problem and the different approaches. Looking at both having bottom-up and top-down processes, so approaching kind of the problem from both directions, where you have looking at the perceptions and allowing the categories and the representations that arise from that flow up to a higher representation, but also adjusting the higher representation and flowing down to the individual items. You have to have some sort of representational capacities in the autonomous agent, and they also believe you need some sort of categorical and an ability to abstract in the autonomous agent. They also argue that the agent should have communication capabilities, and there should be multiple agents. The later work on the practical solution that's introduced by the same authors, they hinge on this a lot. It doesn't necessarily mean that you need separate robots, but you could have separate processes. And this communication requirement, what's interesting about what these authors later introduce, they use a metacognitive approach, which kind of going, if you believe some authors like Nelson, who argues that, well, metacognition is what you really need for consciousness and to make people, intelligent. And if you need that, then you're really arguing that there is kind of like this bifurcated system between the object and meta level. Taddeo and Floridi in their proposed algorithm, they also have, object and meta level agents, but that have to communicate. They talk about an evolutionary approach. Part of me wonders if that's not just a piece of the zeitgeist at the time when evolutionary algorithms were really important. But then again, we've had some of our most recent promising results in AI using evolutionary approach, like again, AlphaEvolve. And then of course, the satisfaction of the Z condition. So again, I think this line of work on symbol grounding is quite useful in helping us think about how to move forward in artificial intelligence, because clearly, statistical based systems, while they're very good at recognizing things and generating text and these kind of tasks, they still don't produce symbol systems that have symbols as part of a symbol system that have a consistent semantics. And so, these insights can inform future directions. And I think the LLMs are an interesting special case where we can look at, hey, should we relax the Z condition to allow for resources like that aren't really producing true symbols, but are producing things that can give us a hint. So that concludes the lecture for today. I hope you enjoyed. Please don't forget to like and subscribe. Thank you.